How does current flow in a circuit with an inductor? The law that governs inductors is a combination of Faraday slash Lenz's law that predicts how a magnetic field interacts with an electric current. To produce an induced EMF. When current flow through an inductor changes a time varying magnetic flux induces an EMF, an induced EMF, but in circuits we call this an induced voltage, and this induced voltage is the voltage of the inductor. According to Lenz's law, the induced voltage by the way, I could have said the inductor voltage has a polarity that opposes the change in the current that created it. That is, inductors oppose any change. They oppose any change in current through them. That's a lot of writing. So let's get a little bit more clear with an example and just try to think about this of how you probably learned about this in physics 4B. So what you want to look at is that suppose we have a bar magnet that approaches a stationary closed coil. We want to go through a series of steps to explain this behavior. Okay, so here's what we're having. So the first thing that we want to look at is that we want to go through this in steps. So we want to suppose a bar magnet approaches a stationary closed coil. So let's go through steps here. So what happens? The approaching magnet increases the flux. So in other words, we know that the magnetic flux, so this has to be proportional to the magnetic field, and we're going to say that instead of writing flux, we're going to say it's just increasing the magnetic field. So it increases the flux or magnetic field through the enclosed coil or inductor. So picture-wise, I imagine that we have a magnet. So we'll say here that the red side here is going to be the north and the green side is going to be the south. So we'll write S and N. And now we know that it's moving in this direction. So you could imagine that if I have a coil here, let's say that this is my coil, and then these are the wires of the coil. That when I look at my inductor, there's going to be an increase in the magnetic flux through here, which we're going to just focus on the magnetic field. So that has to happen. Now, the response of the coil inductor is to generate an induced voltage, which we call the voltage of the inductor, such that an induced magnetic field opposes the increase. So picture-wise, if I still take this image right here and I bring it with me, and I paste it right here, now I have my coil right here. So what's going to happen? I now produced a induced magnetic field that's trying to reduce the flux. As a consequence, there is an EMF, and this EMF, we're going to call this the induced voltage VL. So now, what does that induced voltage do? So 3, to be induced a current must create this. This is the induced current I induced. The direction of I induced is derived from the right-hand rule, which is caused by voltage VL. So if I look at this picture one more time, here's what I'm really seeing here. The only thing we care about is about the induced stuff. So if I look at this, I'm seeing this. All we need to do here is that we don't care about the increase. All we care about what's happening. So now, in order to do this, I have to have an induced voltage right here. And that voltage is VL, which is the induced voltage. And then we say that there is now going to be a current I induced that causes that induced magnetic field. Now, let's translate this to an inductor in a circuit. So what we imagine here is that we have a circuit that's going to look something like this. So I have a source, and the source now has a switch, and it also has an inductor. So we imagine that the switch is then being closed at t equal to 0. Once again, we have a source, we have our inductor. At t equal to 0, the switch closes, right? So at t equal to 0, the switch closes, and now we're asking what happens. So what we should think about is that what does that induced voltage do? So when the switch is closed, the current does not immediately jump from 0 to its final value. And again, the question is, why? The opposition of the inductor's response to the change is greatest at the beginning. Because the amount of change is greatest. The opposition it poses is in the form of the induced voltage VL. This decreases to 0 as the current approaches its final value. We'll talk about those details a little bit later on. The key point is the resulting induced voltage. Has the effect of gradually allowing the current to increase rather slowly than an instantaneous increase. Just to, round out this discussion here, even a circuit that does not contain an inductor still has some inductance. Here's one more example before I close this discussion here. So suppose a circuit does not contain an inductor. As soon as the switch, is closed, there is a closed loop formed with an increasing / changing current. So what happens here is that if I have a circuit, and then here's my switch, and then here I just have an element, some element. So as soon as the switch is closed here at t equals to 0, I now have a current that's going to be increasing. So that means I have an increasing current. And with this increasing current, we could imagine here that I have a magnetic field that's now going to be produced. As a consequence, there's an induced magnetic field that's going to be created. So now I have an induced EMF that produces this current. And so now this magnetic field is going the other direction. So this is B induced, and then right here you have B increasing. So it even happens around a closed circuit with no inductor.